Welcome to Syntax. In this Supper Club, we're talking to Richard Davison. We get into deep all about the new LLRT runtime for JavaScript that they're working on over at Amazon. This thing is crazy fast. In some cases, it can be over a 30 times improvement in cold start time. So we get into all of the details about how this thing is able to be so incredibly fast, how he's putting this together, what you can use it for, what are the ideal use cases for serverless in general, and just all the ins and outs about building a runtime for a serverless platform. So without further ado, let's get to the interview. Welcome to the show,
Hey.
Richard. How's it going, man?
Thank you so much, Scott. Thanks for having me. It's great. Beautiful weather here in the west coast of Sweden. Couldn't complain. It's about 25 degrees Celsius, sun is shining, awesome.
I love it. Love it. So, maybe before we get into any of the LLRT stuff, let's maybe just if you could give us a background on, who you are, what you've been doing, and how long you've been doing it.
Sure. So my name is Richard Davison. I want to call it developer / architect from Sweden. So I've been building with web technologies basically my entire career. So I started out with Node, I think almost 10 years ago at my first real job after university. So we were quite early back then. It was at CGI. So a big consultancy company. We were really early in the Node. I think we in the Node ecosystem, or we started building when it was something. The version was something like 0.84. I don't quite remember, but we were very early on there. So we kind of jumped straight into JavaScript. In hindsight, you could argue if the product or the tooling was mature and everything, but still quite fun. So started doing that for a couple of years. Yeah, it was very challenging, of course, because it's quite different back then than as opposed to how it is now.
It was wild back then. There was no ecosystem. All of the packages were being made, and it's totally different space now.
I don't remember even if there was npm or not. I can't remember. I think that was may have been even before npm. I don't know, but yeah, it was pretty wild. It didn't exist promises or anything like that. I think it was third party promise started arriving, but it was no async await, and not anything that was built into the specification or anything like that. So quite special. So I did that for a couple of years, and we focused on building apps when that was the big thing to do, writing and building mobile apps. And we used JavaScript to build them cross-platform. And there was a bunch of technologies that we used to do that. I think something called Titanium, if memory serves me right, or I don't even know if they're still around, but we used that technology to build cross-platform. That was way before React even existed, or React Native or something like that. Then I transitioned to the e-commerce industry. So also very fun because you get to tackle a lot of challenges, because basically every customer had their own demands and their own requirements, and user experience was the center around everything in e-commerce, right? Because it directly translates to the revenue. So if we can improve the user experience for our customers' website, we can make it faster, more efficient. It directly translated to increased revenue, which was also very, very fun and challenging, especially since the frameworks that we used to do at this other company, that we used to work with on this other company, was a bit outdated. They had a bit of legacy. So I built some tooling around that to try to break them apart into more of a microservice architecture. And finally, I ended up at AWS. I was recruited, I think, 2.5 years ago, something like that. So a recruiter reached out to me and ended up here. So now I'm at AWS building predominantly with modern apps or app mod technologies. So that means serverless and container technologies. And of course, a lot of Lambda is very close to my heart, and JavaScript has been with me this entire journey.
Yeah. So is it mostly JavaScript that you're working on at AWS, or other technologies?
It's a mixed bag. Yeah, it's a lot of technologies. Since I came from this kind of diverse background where basically every customer had different requirements, and they sometimes yeah, sometimes we also had projects that we took over or improved or something like that. So it kind of required you to have a very broad sense of understanding of different technologies.
Yeah.
So we're here to talk about LLRT, which is Amazon is building a new JavaScript runtime. And this is wild to me that we now have way more JavaScript runtimes on the server, like we've obviously have Node, and then we've got Bun and Dino and Cloudflare workers. And I did a whole talk. I think I counted up to 9 of them. And that was before Amazon came out with this LLRT. So why is Amazon building yet another JavaScript runtime? And what is it?
Yeah. Sure. So it's not actually like an official Amazon or AWS product right now. It's still like more of an experimental package. So we're trying to build something that targets a specific set of features that we haven't seen anywhere else. And this is kind of the reason why I came up with this idea internally. And to take a step back and talk about what it is and the rationale around it is, my job also consists of building tooling for partners and customers that work with Amazon technologies. And building tooling can involve everything from making their life easier to making their experience of their end customers better. Sometimes that can even involve building runtimes. Not everybody does that, but I'm a geek, so I like geeking out in things, in technology. But I saw that there was a lack of technologies specifically tailored and built around serverless architecture, or specifically Lambda functions, to have something that was tailored for Lambda functions, right? Lambda is a very capable service. So it basically works by letting customers build a nano service, right? If you take your microservice and break it down into even smaller pieces, we call these functions. So you build small functions, and then you can expose them to the public internet or react on events. So react on things happening inside of the AWS platform. If someone puts something in a database, or if someone puts some data in an object storage or whatever. So it's kind of the event-driven architecture glue. And these Lambda functions can all run different programming languages. And the great thing about them is that you don't have to worry about scaling, or you don't have to worry about keeping them up and running, or resilience, or availability, or anything like that. But we handle that for you. So as the load increases, or as they process more events, they simply scale automatically. So you can focus on building applications that solve your business problems, rather than spending a lot of time on building complex infrastructure. But to be honest, it's quite complicated to get that right? To have, to set up scalable architectures. Yeah.
Well, I'll just give one quick example for anyone listening who's like, I'm not sure, like what that might be. Is like imagine you had an application which at the end of the month it would email a PDF of like a receipt to every single one of your customers, right? Like the old way to do it would be, you would have a server running that makes those PDFs, and you might have some like cron job where it takes 3 days to generate all of those and send them out. And then you're paying for like 28 days worth of server just to sort of sit there while you're waiting for it. With a Lambda or serverless, you can basically just like let that thing sleep, and then for however long you need, you can spin up 1,000 of them and very quickly do all of that work. And you simply just paying for the amount of time that you're using. And then I don't know if you guys use the word spin down, but like it sort of closes out, and now that computer is no longer running, right?
Yeah. That's about it. And it's, the great thing about them is that you're only paying for the compute that is consumed. And it's not like you're paying for the underlying machine that is consuming CPU resources or anything like that. It's actually the time it's spent on processing your event. So it's very, fine-grained. So it's billed per millisecond level, right? So as soon as you get an event in, and that event can be something like Wes described here, where, at the end of the month, you need to create a PDF or whatever. But it can also be an event that reacts to like an HTTP call that is a synchronous event. So someone, hitting up an endpoint, posting some data or requesting some data via GET request or whatever, and then you can respond to that via Lambda function, and it will, expose an API. This is a very common pattern as well. So it's not only processing of asynchronous stuff, so meaning like reacting to things happening inside of AWS, but it's also synchronous stuff being attached to something like an API gateway. You can even expose an endpoint directly to a Lambda function, so you can invoke them without an API gateway, etc. So it's a very versatile service, and it kind of also works as a sort of an extension to a lot of other services. So if you want to add capabilities, for instance, you want to add some custom authorization to an API in API gateway, you can use a Lambda function to have customized code to handle that authorization. We have a bunch of different services that very well integrate with AWS Lambda. So that's one of the major benefits, that you can get quickly going and start building, real value in your product, and rather than focus on building like non-differentiating infrastructure that you just need. That is that kind of accidental complexity that you have to add to your application.
Yeah. In regards to LLRT, like what makes LLRT specifically applicable to that context?
Yeah. I was just going to get to that, and I'm glad you
nice.
asked.
Good. Cool.
Yeah,
yes.
That's a good, cool segue. So, like I explained before here, when we talked about these different programming languages and sort of frameworks that can run on Lambda, you have a bunch of options. So you can run Java applications, you can run Python applications, Node.js applications, .NET applications, and a whole heap of other predefined and provided by AWS runtimes, as we call them. You can also run custom runtimes. So this means that you can build your own. So as long as it's a Linux program, you can basically ship whatever you want. You can even have a Cobalt Lambda function running, right? As long as it communicates with the underlying API, and it's not really super advanced. It sounds advanced, but it's not really. As long as it can do HTTP, you can put it on there, and as long as it runs on Linux, you can put it on there, right? But the thing is that these languages and frameworks, they are built for general purpose. So, Java was created in the 90s, Python was created in the 90s. So they all have a bunch of legacy. And back then in the 90s, the concept of serverless and these ephemeral, short-lived running instances that quickly spin up and like you said, was spins down again and are discarded, that concept didn't really exist. So you started a server, maybe you shut it down when you created, you had to patch it or deploy an update or anything like that. You did that in the middle of the night when there was no users, and then you started it up again and pretty much left it alone, right? So the concept of building for that feature of having fast startup, it didn't really exist. So they haven't the general purpose programming languages and frameworks that exist. They haven't been designed around that premise, right? So they weren't optimized for fast startup. They were optimized for long-running tasks and have good performance when running over a longer period of time. That's not true for every runtime in C++ or C or Rust or anything like that. Are there exceptions? But the exception can kind of be drawn here with compiled languages versus interpreted languages, or languages that has a sort of a cross-platform approach, kind of the same thing. Those are not as prominent to fast startup as compiled languages are. But those are actually the languages that most people use. I mean, there are a ton of people writing JavaScript applications and Python applications and Java applications, right? But they all suffer from this sort of legacy and also from not being so fast to start. It still works really well, but for that low latency, there are not really any alternatives except for going to Rust or C++ or C, even Go, right, to have this more of a compiled approach. But then you sacrifice on flexibility, because you have to recompile in order to change something, and you don't see the source code anymore in a similar way. There is a value of being able to kind of, your source code is also what you execute, right? You run straight off the interpreter, as it sounds. So that's kind of the rationale around this project.
Awesome. Let's talk real quick about Sentry, the application monitoring software for your application. Throw it on it works on your front end, it works on the back end. It's going to give you information and insights into why your application is breaking or why it is slow. All kinds of great information, just like some magic glasses for figuring out what's going on with your application. Check it out, sentry.io/syntax. Right now, people who run Node.js in like a serverless or in a Lambda. I'm actually curious if that's the most popular runtime, if you know that. Do you know that?
It's one of the most popular ones, right? There's a lot of, I don't think I can share or even know all the statistics, but I know, I mean, there's basically, there's a lot of Node.js functions and also a lot of Python functions as well. I think those two are the most popular ones. Then
Okay.
Java and .NET and others. But Node and Python are extremely popular to run on Lambda. Yes.
Yeah. And so people that are running Node in that, like you said, they're hitting like what issues specifically are you hitting? Is it the time that it takes to initially spin up when you've not hit a function before?
Yeah. So yeah, it really depends on what you're trying to build. Or in most cases, this is not a huge deal. And you might experience it, like to your point, like you mentioned, there was when you haven't invoked them in a while. So when you haven't sent an event to be processed, then it goes kind of into a sleep mode, meaning that it conserves resources because you only pay when it's running compute, right? Mm-hmm. So this is sometimes referred to as a cold start, when it needs to provision the resources again. It needs to download your code, your code package that you published to Lambda, right? It needs to download that, spin up a new execution environment. So that is a VM. So every Lambda function runs inside of a virtual machine. But this is a special virtual machine called Firecracker, and it's optimized for fast startup, and it's sort of a super lightweight virtual machine. So it loads the code into this virtual machine, and then it starts it up. And all of this takes a bit of time. And you also provision with your Lambda function code, you provision how much resources it's allowed to have, because it's a linear relationship between how much resources does this Lambda function have versus the cost, right? So the more resources you give it, and this is known as memory configuration. So the more memory you provide to your Lambda function, the more CPU it will have, but also the greater cost. And it's a completely linear relationship there. So twice the memory will give you twice the CPU and also twice the costs. You want to keep the cost down. But that also would contribute to this cold start. But what we have seen here in production metrics is that cold starts aren't really a super prominent challenge, right? Or super prominent problem, because it mainly exists during the development lifecycle. So it typically occurs between 1% to 2% of all invocations, and even less so. So it really depends on your traffic patterns, etc. But it can still be a bit disruptive to this seamless user experience that we want to provide to our end users. So it will be better if we can get rid of them for all. But there's obviously a trade-off. We have to load these runtimes and languages that weren't specifically designed for have this low memory configuration. The lowest one is actually 128 megabytes. So you can imagine Node like spinning up with that. It's
I didn't think of that. I was just thinking, it's faster, right? We have somebody DM me the other day, says, "Hey Wes, I'm from Germany. Sometimes the syntax site is so slow to load, and then after that, it's super fast." And I thought, it's probably the first guy from Germany for that day visiting that, like spinning that up, and it takes a second to get going, and then it's warm, people call it. But I didn't think of what you just said, which is price wise. If you have to do things that don't necessarily need a ton of compute, then you can go for the really cheap Lambda, right?
Exactly.
What kind of stuff would that be doing? Maybe just like redirecting or checking auth or something like that?
Yeah, but it's a ton of stuff actually, because what we see most customers doing inside of Lambda, they write like integration code, or sometimes referred as glue code. They do some data transformation. They maybe massage the data, or remove some unwanted fields, or aggregate data from different sources. And a lot of customers are using or communicating with AWS SDK, or calling downstream services, right? So this is what most people do. And if you think about that, that's not really compute intensive tasks. It's more IO intensive, right? When you're waiting on a downstream dependency. So configuring memory low, also keeping costs low, would make sense here, since you don't want to just charge when you don't need compute. You don't need basically the CPU to do a network call, right? That is in practice, but in reality, it also consumes some. It requires some CPU to do the TLS handshake. When you do a HTTPS call, there's TLS, there's encrypted traffic. It has to create a secure connection, and there's a bunch of data flowing back and forth. And there's like a ton of optimizations around that you can do for the people that are really into Lambda and know about all that stuff.
Okay.
Have optimized that heavily, but it's still required. So if I can remove a bunch of things and create a custom runtime that is super lightweight, and that starts fast, and has the most important things that you would do, or that a lot of customers are doing, if that can be created, it's maybe worth the trade-off of not having the full API capabilities like Node or Dino has.
Yeah.
So just to be clear, LLRT is not meant to replace Node or Dino or Ban or anything like that. Those are very ambitious projects.
Yeah.
And I'm very impressed on how far they got in all of these projects. There's no way that this can ever achieve the full compatibility, and that's not the design either. It's meant to complement them where you want to have this really low latency. And to be honest, right, the simplest way of making things faster is to not do as much, right? So if I can remove APIs, and if I can create a lighter runtime, then I will have faster startup by doing that. So if Node just removed a bunch of APIs, quite honestly, it would be much faster.
Yeah.
But they don't know, they can't do that, because people are dependent on those APIs, and they don't know what APIs are being used. So I have an advantage here. I can say I only support these, and if it doesn't work for you, then you can use Node.
Yeah, no kidding. The benchmarks in the GitHub repo, at least, are really pretty wild, especially for the cold starts, like you mentioned.
Yeah.
Especially when compared to Node, it's shocking.
Yeah. Yeah. Like, for an example, a cold start on an HTTP request is 155 milliseconds versus 48, right? And that might not seem like a lot. I guess 100 milliseconds is a lot when you're talking about somebody sitting there waiting for the page to load. But if you're talking about paying by the millisecond, I'm sure there's customers at Amazon who are salivating at this, being like, you're telling me we could cut our bill by 3 when you're really splitting hairs there, paying by compute. I'm sure they could save quite a bit of money. Is that true? I'm just guessing here.
Yeah, and it's actually even more so. So if you look at there's benchmarks on the repo doing a very simple thing, but also a very common thing. It puts some data onto our serverless database, DynamoDB. We have a multi-column key value store called DynamoDB, where you can store data in a serverless way as well. So it works really well with Lambda. So the example just puts the event that gets sent into the Lambda function. Remember, we're processing events here. This can be HTTP or whatever. And it puts the data into DynamoDB and just returns an OK response. So running that with Node 20 here, you get, for a cold start, it takes inside of Lambda, it takes around 1,400 milliseconds for the best case. And in an LLRT, it takes 50. So that's like, 1,400 divided by 50. It's like 28 times faster, right?
Wow.
For the fastest case. For the worst case, it's something like 15 times. And, what's the trade-off? The trade-off is what I briefly explained before, is that you have a limited API.
Yeah.
You have a very limited API, right? And
for crazy savings. It's just outrageous.
For crazy savings, exactly. Yeah. So it's not only for cold start, it's also for warm starts. And there's a couple of reasons why this can be so fast. So the major reason is this is a completely new project built from the ground up. So I don't have to adhere to all the compliance and all the backwards compatibility that Node has, right? So it's I've cheated a bit here, right? I can build something from scratch, but I can also tailor it for serverless environments. I know what CPUs it's running on. I can enable features inside of the runtime that only works for those CPUs, like SIMD, that is single instruction, multiple data, very advanced, like low-level CPU instructions that can work effectively with lots of data at the same time. I can also use Rust, which is a compiled language that is also very optimal, very fast, instead of JavaScript. So the runtime itself is actually implemented in Rust, and it uses another JavaScript engine that is written in C. So in Node, for comparison, and also Dino uses V8. And V8, you've talked about this many times on the show, but it's an engine from the Chrome browser. So it comes from Chrome. Bun uses a different engine from the Safari web browser or WebKit. But all of these engines, they are very complicated. They are also very capable, but they also tailored for longer running tasks, or they have best performance over things running for a longer time because they were built for web browsers. When you open YouTube or open a website, you're not going to stay in it for 150 milliseconds and then close the tab, right? You don't care about that as much. Of course, startup is important, but not really as important as it is for that long running sustained performance. So they're all built around that premise. That has some implications when running on startup. So I would rather save the compute used for optimizing the code that is running inside of V8 or JavaScript core to run my code of the interpreter, so meaning that run straight off the source code instead. And a couple of ways of how that is done. I don't know if we can if we should go into that, but there's a bunch of techniques being applied. But the main reason for the performance gains is basically this super lightweight engine that I'm using, built in C, called Quick.js. So it's less than 1 megabyte in size, and it supports ECMA 2023, so a very recent standard, ECMA standard. And in comparison, I think V8 is something around 20, 30, or even 40 megabytes. So it's like 40 times more complicated than Quick.js, right? So just that in itself will contribute a lot to the fast startup.
And the developer behind Quick.js is Fabrice Bellard, who is also the author of FFmpeg, amongst a million other things. Like just a genius. I remember a while ago when they started talking about Quick.js, I'm like, oh, it's kind of interesting. Like maybe you can throw it on an embedded device, but like, is it really gonna are they really gonna implement all of JavaScript in this thing? And it's amazing that it is, right? Like, so they implement the JavaScript language, which is things like variables and functions and async await. And then it's your job then to implement runtime features like fetch. Is that right?
Yeah, that's exactly right. So an engine is not a runtime. So similar to a car, I mean, and the engine is what kind of powers the whole thing, but it doesn't have a lot of APIs. So you have, like you said, the underlying like fundamental components. You have the variable declarations. You have the whole scoping, global scoping and function scopes and function execution and all of that. And you also have arrays and array buffers and all of those APIs that exist under like the primitive types and also some of them, ES6 kind of types with typed arrays and all of that. But it doesn't contain anything other than that. So there's no fetch, there's no console even, there is no no file system, nothing, no sockets, no. You have to, basically everything that you import from Node when you have an import or a require, that doesn't exist. So basically what you have in global scope is what you have inside of the Quick.js engine. Quick.js itself is actually also a small runtime that exists as a separate piece of the engine. So you can actually use it kind of standalone with the console, but that's not being used in LLRT. So we're only using the engine because Quick.js runtime is very lightweight and it's not really tailored for for the same use case. So all of those APIs are now implemented in Rust, which means that they are really, really fast. In comparison with Node, most of the APIs are actually implemented in JavaScript. It's only the low-level stuff, like timers and things, and the event loop and all of that is implemented in C++ for Node. But you have the majority of all APIs are in JS, which kind of, if you remove some of the features of the V8 engine, like a just-in-time compiler, that would not perform very well because it's built around the promise of that.
I see.
Richard, I gotta say, you've been hitting our show note questions. Like, we have a list of questions to ask you, and every single time I'm about to ask a question, you answer it already. So it's pretty amazing here. Just wanted to shout that out.
Awesome.
Do you know what other use cases, or I've been trying to get Fabrice on the show because I want to ask him, but I'm curious if you know as well as why did he make this? Why did he make Quick.js? Was there a certain problem, or did he just think, I wonder if I can write JavaScript in C?
Yeah, that's a very good question. This guy is a magician. I think he has to be one of the world's, if not the world's best programmer. If he sees a problem, he's like, I'm going to do it better than anyone else. And he creates FFmpeg, or he even created a Windows emulator in the browser that can actually run Windows XP in JavaScript, which is
where would the world be without FFmpeg? It's like,
yeah. He's absolutely, it's insane how talented that guy is. It's I can't even fathom how, his skill level is beyond anything I've ever seen before. It's he has a website that is basically just like a text file of all of these amazing projects. That is PC emulator in JavaScript, JS Linux. That's awesome. I mean, you should put that in the show notes.
Definitely will do.
Fantastic. That actually boots Windows XP like the real thing. It's like a kernel in JavaScript, and that's and here we are writing, people struggling with understanding effects in React, and I do too, right? And then
I struggled with a set timeout inside of a React hook the other day, and I was like, there's people running Windows XP in the browser.
We are not the same. Own kernels. The kernel in. I'm like, what is a kernel? Oh yeah, okay. Then this guy is
That's cool. It always makes me feel good though when people like that see JavaScript and go, that is a good language for regular people to use. And now let me build something that is very hard so that regular people can write a JavaScript function and get some major benefit out of it.
Yeah, and it can run on embedded devices or whatever. I'm not sure if that was the reason why. I don't actually know. I think maybe he just, he likes doing these crazy challenges that nobody else has done before, and then just make it, super, super good. But it's actually being used. I think Minecraft uses this inside of their scripting thing when you communicate with the Minecraft world or whatever. It's being used here and there. And nowadays they even run JavaScript in space, right? The James Webb Space Telescope runs some weird runtime, I think. Not Quick.js, unfortunately, but there's some old thing. I don't know why, but it seems a bit risky. They get undefined and the whole thing crashes in space.
So back to LRT. You said it's built with Rust. What made you pick Rust specifically?
I wanted to have a compile language. That was basically a requirement as a foundation, right? I wanted to have a compile language that was, super fast, and also something that was kind of rather, I could be effective with. So I picked Rust, and I kind of instantly regretted myself because I'm like, I can't. I fought as much with the compiler as it helped me, or with the tooling. So the learning curve is very steep. And I've done some Rust projects before. This is not my first Rust projects, but initially when I started with Rust, almost I think everybody else struggles a lot. But then it kind of loosens up a bit, And I very like the fact that the Rusts help you write safe code and safe that is being memory safe. So a lot of these really high performance compile languages have problems where they give you a lot of control, but you also have to keep, you have to make sure that you're doing the right things. Otherwise, you will get a runtime error. And the runtime error is not like in JavaScript where it says, oops, this is undefined. The whole thing crashes, right? It's an unrecoverable thing. The most common one of those things is if you have a memory access error, right? You're trying to read or write to memory that has not been allocated or has been freed. So when you have to allocate memory and stuff, all of that, I wanted to, that sound a bit too risky and too complicated. I don't want to do that, but I still want to have performance. I don't want, and it's also quite mature. I think it's been around for like 10 years now. So it has a huge ecosystem. So that was some of the kind of the ticks I wanted to have before when picking a compiled language or like a foundation for this project. I want to have it to compile to be super fast because performance is key, right? And I want it to be mature. So they kind of ruled out like SIG. Go is pretty mature, but it isn't as performant as Rust, arguably. And it also uses a garbage collector. I don't want to have that because it can add pauses, right? I want to have consistent, fast performance. So it was pretty much Rust, and I had some prior experience, and I could be somewhat, at least, productive. I think I'm a lot more productive now than I was when I started the project because I spent so much time in it. But it's still, I think it's a great language. Hard to learn though. That's why I built LLRT so people can still use JavaScript and have similar performance. Not same, but similar.
Mm-hmm. Yeah, that's great. That's why, like the higher you go in the ease of using a language, it's a trade-off, right? You always give up some stuff in order to make it easy to use, right? And here we are, me and Scott at the end of the line, just using JavaScript because that's the best our little brains can do. But underneath, right? Like it's eventually it goes down to ones and zeros and runs on the silicon.
Yeah, it's crazy actually when you think about that, like how many abstraction, layers of abstraction that there is actually. So you mean you have nowadays you're talking on top of the stack. I don't know. Is there something that produces output TypeScript? I don't think it is. But say that TypeScript is on top of the stack, then TypeScript is transpiled into JavaScript. So that's kind of a semi-abstraction. I don't know, right? And then you have JavaScript that sits on top of something in the browser that has a runtime that is written probably in C or C++, which is an abstraction over assembly or other things, right? And assembly is also an abstraction over like the instruction set of the CPU, because assembly is also like, believe it or not, an abstraction. And then you have the actual like machine code being executed, which is all being held together by silicon that is made in like a factory nanometer scale. I know it's
wild,
amazing how this whole thing, this card house or whatever, holds together. Because it's amazing. So many layers.
Anything works. I was talking to a guy who works at one of these camera companies that provides like very high end security cameras for like police cars and things like that, and he writes the C code that runs on the camera. And he's talking about like just processing. He's like, we don't even talk milliseconds in the office. It's nanoseconds here. And here I am on the opposite end being like, oh, we have WebRTC. I can hook up my webcam and get access to it in the browser. And it's crazy that they're so far apart from each other.
Yeah. It's a similar with like stock exchange, right? When they talk about, if they have a millisecond of latency, people lose a ton of money, right? They have to be. They even move like the server closer to the exchange because the bandwidth or the data transfer is faster because the physical location is absolutely massive. And I think a lot of those like stock exchanges, they are in C++, but also I've heard that a lot of them are actually Java, because Java is, again, really good for these long-running tasks when it kind of auto-optimizes itself thanks to the just-in-time compiler that is constantly being running and optimizing the code. So if like a Java program has been running for a really, really long time, it has similar performance, sometimes even better than C++ or C.
Really?
Yeah, it can be. It not always.
Like
Have you seen like the?
it
Sorry.
gets better over time. Like it gets faster. You said if it's been running, it's like a fine wine. My Node apps
Yeah.
just get slower if they run for a while.
Yeah, you got a memory leak. Yeah.
Yeah, exactly. They actually do, because it's of course this is a bit depends on many things, but in general, the concept of a just-in-time compiler. So Node also has one because it's inside V8, and similar Dino uses the same thing. So a just-in-time compiler is exactly what it sounds. It's like a compiler that is built into the runtime itself. So Java has a Java virtual machine. It's a runtime. It has this just-in-time compiler that takes the Java bytecode. So similar to how JavaScript is executed in Node, it analyzes like the parameters sent to the function and the actual function code that is in there, what path it takes, what branches, like what if statements, etc. And then it generates optimized machine code. So like real compiled code, it generates on the fly automatically. And depending on what arguments are being passed to it and how it's executed. So say there's like an if statement that is almost never executed, it will get like compiled away, so it can be more efficient. C++ and other compilers also does this, and you can give it hints and say that this thing here is like a cold path, so it's not very likely to happen because the compiler doesn't know always, right? But this happens automatically for both JavaScript and Java running their code. So Node does this, Dino does this, Bun does this as well. So it constantly tries to optimize. So if you're running it for a really, really long time, you will have a huge performance benefits. That's when you do this, JavaScript benchmark, comparing one JavaScript doing, hashing or something in JavaScript and comparing that with something else. So running that in LLRT, for instance, if you compare doing like 1 million iterations of a loop, that would suck in LLRT. It would have horrible performance because it doesn't have a just-in-time compiler. But on the other hand, like doing hashing and things, all of that is implemented in Rust, so we'll have the most epic performance. Whereas in Node, many things are in C++, but many things aren't, right? So it might not even be faster. But a just-in-time compiler is generally much, much faster over time. Hence, the stock exchanges uses these really powerful machines that have all of its methods and functions been running for thousands or millions of iterations and have been super optimized automatically.
Okay, that makes sense. Man, it's we talked to Jake from Fastly, and he kind of does the opposite, which is they try to compile your top level code beforehand, so that you don't hit that just in time. Sort of
you can actually do that. There's like a compile cache in V8, so you can run code, and then you can tell Node to dump the V8 compile cache. So like all of the compiled code that V8 has stored in memory, you can dump that to a file, and then you can restore that like next time you start a program. So that will save a bunch of time not having to analyze and try to figure out the optimal way on how to compile your JavaScript code. What can happen though, and that often happens in runtimes with a just-in-time compiler, is something called a de-optimization. Since we're now, the runtime makes assumptions on how the code is being executed. What if those assumptions are untrue? Well, then it has to, recompile and throw away the old compiled code, and this is really expensive. This is one of the reasons why you see sometimes in Node, you see fluctuating response times for doing exactly the same thing. You can't figure out why. Oh, why does this take, it took 200 milliseconds this time, but only 50 next time. What is happening? This is usually an effect of the optimization that is happening. And it's especially prominent if you have low resources or few resources, because it can't keep everything compiled and optimized because it's memory intensive, right? It has to evict things from its compiled cache. So that's often what we see inside of Lambda, especially because you have, you want to keep the memory low. So you tweak it down, and then the Node Runtime has to struggle in trying to figure out, okay, what method should I keep in my compile cache? This one is maybe not executed so frequently. Let's throw it away and then recompile it again. And now I'm sacrificing precious CPU, and it costs money and it takes time.
That's super interesting, man. I'm learning a lot about how like the lower level stuff works. I really appreciate that. I want to ask one more thing about the Node Compat. You said like this obviously is not going to be a Node replacement. It's good for things that it's good for. But if you look at the Compat matrix on the docs, it's actually pretty good in terms of like what APIs are supported. What are some things that would not work well or at all in LLRT?
Yeah. So first, if you look at that compat matrix, it's a bit, it has a few exclamation marks. So when we say that we support FS, right, we're not supporting the full FS API. It's partially supported. So we kind of also, by design, try to support what things that our customers and users actually are using. And we see sometimes we get requests. I need to have this because, reason A, B, or C. And then we try to consider it because every API we add, it adds to the weight of the runtime. So we would make it slightly slower for every one of those APIs that we implement. And it also naturally takes time to implement them. But that being said, we do support a lot of APIs. We support like most of the things that you need from FS promises, but we don't support the regular callback FS module, right? So you would have to, I would have to change my code to use FS promises, which I think arguably that you should. Because I think it's a bit nicer to use async await rather than callbacks and promises. That being said, LLRT has designed its APIs with the same specification as Node. So when we have like FS read file, we use the same signature as Node. So when you want to use like an API that is not supported, you can switch back to Node. And you haven't wasted any effort. And that's just, a major decision that we took early because we don't want people building specifically for LLRT. Ideally, we want, but we don't want them to have that risk. We need to earn the trust, right? We need to say, okay, try this out. If it doesn't work, or if you in the future have a new requirement, you can't rely on us, implementing that. Then you can switch back to Node, or move that out to break that apart into two separate pieces, but you should not waste effort. That's a very important thing, right? It should be relatively simple to transition. So that's one of the major downsides.
So
of course,
no custom APIs in LLRT. Whereas Bun and Dino have their own. There's no standard FS API, right? So Bun and Dino have implemented their own. Node has their own. And you're not going to come around and make a fifth API that we need to do.
No.
Will you try to target the WinterCG spec, or is that too large of a thing for the project?
No, that's the plan. And also, I forgot to answer this from your previous questions. Some of the things that doesn't work, right? So,
sorry.
So WinterCG is like the long-term goal. Ideally, we could meet it this year. It depends. The spec is also still a work in progress. There's a few things in there which is a bit weird for our use case, like WebAssembly functions, right? Executing WASM. That basically for LLRT would require us to embed like a WASM runtime. So now a runtime in a runtime and communicating between the two. That might be out of scope and a bit too complicated here. The other thing that is currently not working very well is streams. So the web streams API is enormous. It's a huge API. You can actually pull in like the streams from Node. It's actually a separate package on NPM that you can use to the same implementation that Node uses. It's huge. It's like 8,000 lines of JS and a lot of edge cases. And you can imagine that wouldn't run very well without the just-in-time compiler if you have a lot of bytes flowing through transformer functions or read streams, write streams, and being piped in between and everything. So ideally that should be native, but it might not be feasible in implementing that huge API in a native fashion. it might be a bit too complicated. So we might have to find hybrid in between, right? So the Streams API is obviously a must. Otherwise, you can't, download larger files than what you have in memory if you always read it into memory, right? So this is something that we're working on, but to try to find like a sensible approach to not kind of go crazy on scope, but also have good performance. So this is one of the trade-offs right now. There's no stream support. You can use some features from streams. We embed that JS API, that 8,000 line JS, but not everything works. Like you can't extend the streams. You can't like use some of the lower level APIs. Doesn't work really well, and they aren't properly tested. So it's still a very experimental work in progress.
The Streams API is huge, and like there's you can if you start reading a stream, it's locked, and you have to tee a stream if you want to be able to read it. And like, whoo, I do not envy the person who has to implement that.
And even understanding how it works. I mean, I thought I knew streams. Then I started looking at the specification and under the hood stuff, and it's like, whoa, this is really complex. So it's like it has a flowing mode and a paused mode, and it depends on how much should be read into the buffer, and it has an internal buffer that gets full, and depending on how much you read, that buffer will be. It's extremely complicated. I made like a semi-light version of it for child processes, not with all features, but it's most of the things that you need, so you can like react on data and things like that from child processes, because I think it's really important to be able to use that. So you can run FFmpeg in Lambda with LLRT and get low latency, right?
Oh,
even stream the output from
that,
from FFmpeg encoding, right? You can do that, for sure.
That would be great. We have to run it in what do we run it in right now?
AWS, I hope.
It is an AWS. It's
media
not Michelle,
encoder, right?
Okay, no, it's not media encoder. It's why am I forgetting the name of this? It's running native stuff on inside of JavaScript. WASM. We're running it inside of WASM, and there's a performance hit there, and there's also limitations for file size, but the trade-off was worth it. What about WebSockets? Is that implemented, or is that something that needs to be implemented?
Yeah, I think it needs to be implemented. I'm not sure if it's in the spec or not. I think it is. I have not started working on that, or the team hasn't started working on that specifically. But I think it should be in there because it's something that people use a lot. We do have some basic socket support. So we have some TLS socket support, obviously with the lack of a full Streams API that makes it a bit clunky to work with. But we have TLS, not TLS sockets, but actually raw sockets, right? So they're not running behind a TLS connection. So that means that they have to be unsecure, but you can expose like a simple HTTP server like internally and have the TLS in another layer if you want to. It's not super complicated to add in TLS, but that kind of adds on top of Streams. So there's a lot of things that depend on having a complete or more complete Streams API than we support right now.
Wow. So do you see a future where this will be promoted to be like an official AWS product at some point, or is it just an experiment?
I sure hope so. It's a bit too early to tell right now. Obviously that comes with a lot of like more guarantees about SLAs and support mechanisms and structures and organizationally as well, but I hope so. But I couldn't tell right now if that will happen. Hopefully it will, and I stay very positive. And we're discussing this obviously internally as well, because we've seen that there is obviously a need. People have been really receptive, and I think there's room for something specific. And ideally, once WinterCG reaches a bit more maturity, people can pick and choose, right? So they can get more guarantees on their workloads. So they can use LLRT when running on Lambda. They can put the same thing, run it on their local machine in something else, and it will behave and work the same way. And by the way, LLRT also works on your machine if it's a or not a Windows, if it's a Linux or Mac machine. No Windows support yet. It could be added, but that's not a priority as well.
Yeah.
But
Man, I feel like my brain grew like 3 sizes
Yeah.
in this conversation. I'm always very interested to learn about the stuff that's a little deeper than clicking buttons and making loops, you know? So that's been fantastic.
Yeah,
Let's move into the
awesome.
last section that we have here, which is sick picks and shameless plugs. Not sure if you came prepared with either of those.
Oh no, I didn't come prepared for that. That's oh,
Okay. Well,
listening to too many of your shows. I'm
can we put you on
overcompensating.
the spot for a sick pick? I guess you know
I
what
would
it
have to
is.
say then Quick.js engine for a sick pick. I mean,
All
Oh,
it's
sick.
right.
or everything. Can I say everything that Ballard has made? It's it's a huge sick pick. Or the JS Linux. There are too many sick picks there, right? So shameless plug. Oof, that's a good one. I don't know. I don't know. Maybe people bashing on JavaScript too much, right? Because they say that no, it's not like performance, it's not the good, or why are people trying to build all of these really advanced tools around the language that wasn't purposely built for running on the web or not running on the web, but running on backends or running on whatever. And I think that's a bit of a shameless plug. I mean, people loved to use the language; they're really productive in it. I think it's a great. It's easy to learn, write, and read, and it gets evolving all the time. And there's a huge community around it, an ecosystem, an npm or JSR and all of the innovation that is happening. I think it's fantastic. So, shameless plug on people bashing on JS. I guess pretty
I like
weak
that.
one, but yeah.
No, beautiful. I like it. I agree too. Awesome. Thank you so much for coming on. Really appreciate all your time. This was fantastic, and I learned a lot.
Yeah, thanks so much, Richard.
Awesome. Thank you guys. See you. See you in the next one.